This example is going to investigate in a little bit more detail the case of resonant forcing. So, examining an ODE that we've been looking at for a while. This ODE is associated with savings at interest rate R1, where the rate at which we save also increases at an interest rate R2. And just for the sake of argument, we imagined that R1 was greater than R2. It doesn't really matter which one is greater. We would like to think that we can earn more on our investments than our annual salary raise, which basically keeps pace with inflation if we're lucky. So we'd like to think that R1 is greater than R2, but the math doesn't really care. And we saw that this equation had the following solution. It had a homogeneous solution, C e to the R1t, and it had a particular solution, which we could find using various methods, of S over R2 minus R1 e to the R2t. And we also had an initial condition, x of 0 equals 0, which gave us the solution, the solution satisfying the initial condition that x of t equaled S over R1 minus R2. We switched the signs because we also then did e to the R1t minus e to the R2t. And this was a solution that satisfied that initial condition and this non-homogeneous constant coefficient linear first order ODE. Now, we had this solution, this general solution for any combination R1 and R2. We saw in class, however, that the method of undetermined coefficients fails if R1 equals R2. Because if R1 equals R2, then the forcing, let's call them both R. If they're equal, we don't have to have 1 and 2 anymore, we'll just call them R. And the forcing e to the RT would be exactly the same as the homogeneous solution e to the RT. And we called this situation resonant. That term is typically reserved for second order ODEs with oscillating solutions, but from an abstract viewpoint, we'll use the word to describe any case where the forcing has the same form as the homogeneous solution. We saw in class in that case that we couldn't use the method of undetermined coefficients. We had to use variation parameters. So the homogeneous solution is still C e to the RT, where R is now equal to R1 and R2. But to solve for the particular solution, we had to use variation of parameters. X p of t is some unknown function u times e to the RT. And when we insert this guess, not really even a guess, it's a syntax trick, as we've talked about, any function can be represented in this form. But when we insert this form into the ODE, we change variables from an ordinary differential equation on an x, and we get du dt e to the RT. Some things that cancel equals s e to the RT. Now, dividing both sides by e to the RT, we get a very simple integral for u, du dt equals s, and so u equals st plus an integration constant. That means that x of t is s of t times e to the RT, st e to the RT, plus an unknown constant times e to the RT. So our particular solution now has t times e to the RT. When we have resonant forcing, the particular solution ends up being a power of t times the homogeneous solution. And if we quickly satisfy the boundary condition here, when t equals 0, c must also equal 0. So x of 0 will be 0 plus c, implying that c equals 0. And so x of t equals simply st e to the rt. Now, the question is, why is this solution so much different looking than that solution? We have this range of possible values of R1 and R2, and for any possible combination of R1 and R2, except the fact that they're equal, we get this solution. This is true for any R1 not equal to R2. Why is it that when R1 equals R2, we get this special solution form? So I want to show you something. It looks like this special choice R1, R2 is giving us something totally crazy and different. I want to show you that it's not all that different. So we have the two forms. R1 not equal to R2, and when R1 equals R2 equals R, we simply have st e to the rt. What I want to do here should be familiar to you from calculus, although you might be a little bit rusty. I want to take a limit as R1 approaches R2. So I want to consider the limit as R1 approaches R2 of s e to the R1t minus e to the R2t over R1 minus R2. Now, how can we probe this limit? I like to do a slight change. I like to say that, say, epsilon equals R1 minus R2. And so as R1 approaches R2, epsilon goes to 0. This is the limit as epsilon goes to 0. And I'll rewrite my R1s as R2 plus epsilon. So this is just a change of variable. I'm replacing my R1s with R2 plus epsilon. Epsilon then is something going to 0, the difference R1 minus R2. So the limit as epsilon goes to 0 of s, what do I get? E to the R2 plus epsilon t minus e to the R2t over R1 minus R2, that's epsilon. I can rewrite that. This is e to the R2t times e to the epsilon t minus e to the R2t over epsilon. And this e to the RT now doesn't depend on epsilon. It's a common factor, and it can be pulled all the way outside of the limit. E to the R2t times s times the limit as epsilon goes to 0, e to the epsilon t minus 1 over epsilon. Let's think about this limit now. We've gotten all the stuff out of it that doesn't depend on epsilon. What does this limit do? As epsilon goes to 0, e to the 0 goes to 1. Minus 1 is 0. So we get a 0 on top. We get a 0 on bottom. We use L'Hopital's rule. Equals s e to the R2t. Limit as epsilon goes to 0. L'Hopital's rule applied to the top gives us epsilon e to the epsilon t. Oh, sorry. L'Hopital's rule, we take the derivative with respect to epsilon of the top and the bottom. Epsilon is the thing going to 0. We take the derivative with respect to epsilon. We get t e to the epsilon t. We take the derivative with respect to epsilon. We get 1. And this limit, as epsilon goes to 0, is perfectly well defined. Epsilon goes to 0. The top goes to t. The bottom goes to 1. st e to the R2t, which is exactly the solution that we got in the case when R1 equals R2, when we just called them both R. So it looks like you get a totally different form of the solution, but in fact, in the appropriate framework, when we take the limit of this solution as R1 approaches R2, we in fact get the second solution. So there's nothing too tricky or mysterious about this. this function just has an interesting limit as R1 approaches R2.